Yeah, so it's a really great honor to speak here. I'm kind of just close enough to Akshay's work that I can understand some of it, and it has been extremely inspirational to me. And I also really respect this decision to have a conversation about where we're going, and I really enjoyed his thought-provoking essay. So I'm talking about a kind of small piece of this puzzle, which is what we as working mathematicians can expect from deep learning. So deep learning is this kind of very simple idea that has had pretty spectacular applications throughout science and industry in the last kind of 10 years, but it's had relatively little impact in mathematics. And I think I'm beginning to understand why, and I'm also beginning to understand the types of problems which deep learning may help with. And so I'm going to try to explain that today. Okay, so I just want to start with a little metaphor. It's very much responding to Akshay's essay. So here's a nice little theorem. There are infinitely many prime numbers. We can think about proving this theorem. So there are we assume there's finitely many. We take their product, add one, and you know the rest. I think it's fascinating to think where that step 2 comes from. Basically, everything else in this proof is obvious, but there's this very non-obvious step 2, which is really an idea. And what I want to explain is that deep learning in a few instances has, together with mathematicians' expertise, led to what I think is a genuine idea. And I'm not at all saying that deep learning can explain these ideas in general, but I will try to convince you that it can sometimes provide the germ of an idea to an expert. So I also want to just kind of put this in the broader context of what I think this conference is about. So there's this very beautiful recent article by Claire Voisin. I'd very much recommend that if you haven't already read it. So she's describing the mathematical process, and she says there is the monastic introverted period where we are just contemplating the ocean of our ignorance, but then suddenly something happens. The monk becomes busy and excited, in a hurry to look more closely at the details. It's a really beautiful description of the mathematical process, and I tried to make a kind of picture of this for a public talk I gave a few weeks ago. So this is trying to kind of picture the mathematical process as a tree, inspired by Claire's article. So we have this period of basically being stuck, and then we have this idea that kind of leads off all these sparks. This would be step 2 in this proof that we just discussed. A lot of these ideas don't lead anywhere, but eventually we get to the point where we're reasonably sure and we're checking details. And I would see the automatic verification as being in the checking details phase. And what I'm talking about is very much in the kind of germ of an idea phase. Okay, so they're 2 very different aspects of the mathematical process. I also just want to give a brief, the plan. So I want to explain for about 15 minutes or so what deep learning is. I'm not assuming you know what deep learning is. I want to give a few simple examples in mathematics that I believe are very illustrative for what deep learning can and cannot do. I don't think we have enough of these simple examples. I want to discuss what I believe is a big myth around deep learning. Just give some tentative advice for anyone that's interested in pursuing this, and discuss the role of scale in machine learning. And then I want to give some examples. Okay. So I also want to give a disclaimer. I'm a pure mathematician. So I'm basically around representation theory, algebraic geometry, number theory, topology, etc., that kind of world. And I've been working with DeepMind for 2 years. So we're interested in interactions of AI and mathematics as a kind of 2-way street. So can machine learning techniques help mathematicians, and can mathematics provide interesting testing problems for AI, or can mathematics push architectures used in AI? So it's a two-way bridge. I am not an expert. Okay, I've been doing my best to understand, but I'm not an expert. I've been thinking about this for 2 years, not full time. All opinions are my own. Okay, so let's get started. So a crash course in deep learning. So one of the things that deep learning can do very well is recognize a tiger. So you can put in a whole lot of tiger, non-tiger images, and it can tell you after training very well what is a tiger and what is not. And if we zoom in on this process, so we zoom in on a tiny piece of this tiger and then convert those grayscale values to numbers between 0 and 255, we get a massive matrix. So our question is, input a massive matrix, a 10 million parameter matrix, and output a scalar value which is correlated with being a tiger or not. Okay. So this is what the deep learning framework looks like. We have our input on the left. We then apply a linear or an affine linear transformation to this input. We then apply ReLU. So this is the rectified linear unit. So this is a very simple framework. I'm not saying that all of deep learning looks like this. Is just the kind of simplest example of what is done in this subject. So ReLU is a non-linearity. So what we do is we fix bases everywhere. So when we get to the second stage of our neural net, we just have a whole list of real numbers. And if they're less than 0, we replace them with 0. And if they're bigger than 0, we keep them. So this is the ReLU, and then we apply another linear map, another ReLU, another linear map, etc. And this is meant to very, very loosely imitate a neural net in the brain, very, very loosely. Okay. So another way of thinking about this is that we have parameterized in a rather convenient way a whole lot of piecewise linear functions. So each of these, we review the ReLU layer as fixed, does not change. The linear layers are matrices, and so depend on a whole lot of parameters. And as we vary these parameters, we get different functions. So we have a massive vector space of piecewise linear functions. And then what we do is we take a target function, phi tilde, and we try to approximate phi tilde by one of our piecewise linear functions. Okay. And in order to do this, we generally do something called stochastic gradient descent, which means that we have a whole lot of pairs of points in our source space and an image under phi tilde. So this is called the training data. We take some random subset of this and measure the distance between phi and phi tilde. So this is called the loss function. And then we use this, we compute a gradient, and then use this to update our parameters of phi. And we hope in this way, we hope two things. Firstly, we hope to approach phi tilde. We hope to get a good approximation of phi tilde on our training points. But more importantly, we hope that if we take other values that are not in our training set and also evaluate phi on them, this will give us a good approximation of phi tilde. So that's the generalization of the neural net. So that's the very important thing. Does our neural net actually generalize? Okay. So often you train neural nets that are massively over parameterized. So it's very possible for this training to learn the training data off by heart, kind of thing. You've got an enormous number of parameters, so you can learn a small number of values easily. But the remarkable thing that happens is that in several instances, this learns a function which actually has predictive power away from the training set, which is the miracle of deep learning. And yeah, I won't go too much into what this loss function is. It's some measure of distance from your target function to the function you've computed so far. So in many cases, you use cross entropy. So you're viewing the output of this neural net as being a probability, and then you want to measure the distance between two probability distributions. I also should say, please don't hesitate to interrupt me if anything is not clear. So I'll just show you a few examples of actually training a neural net in some simple examples. So here, on the right-hand side, you have the training data. So that's the points. So we want to classify these training data into orange and blue. And so in this particular case, we as humans can eyeball this immediately and see that we have a blue kind of clump inside an orange clump. But you could imagine these points might be in a very high dimensional space where our human capability is not able to instantly see what's going on here. And the shading in this picture is the function coming out of the neural net. So this is initialized using some initialization scheme. And so initially we get just a random piecewise linear function, and then we can watch it train. So here I'll show you it training. Okay, so here it's quickly learnt in inverted commas to separate the blue and the orange dots. We can do this a number of times. You can see everything is stochastic here. So the initialization is stochastic. The gradient descent step is stochastic. So every time you run this, you get a slightly different answer, but you hope that you get some reliable answer across different training sessions. Here we go again. Okay, so as we're training, we're wiggling the weights of the neurons, which are the parameters in our linear maps, and hoping to converge to something reasonable. So here I'll show you it training on a more complicated data set. So that's one more time. So here's a more complicated data set on the right-hand side, this spiral. So again, we can see very easily what's going on as humans. And here, in order to get this to train it all well, I need many more parameters on the left. So you can see here I only had 2 layers, whereas here I have 3 layers and I have many more parameters. And here you can watch it training. Okay, so, yep, so you can see it, kind of typical aspects of training are visible here. You can see it struggling at points, and you can see it going through long plateaus of very little improvement. And then you can sometimes see sudden improvement. One thing that I've definitely experienced is often you kind of give up on a model too early. So sometimes things can actually train far beyond when you think that there's no hope. And you actually see this in this case. So after a while, this gets rather good. And of course, with more parameters, this would get more and more accurate. Okay. So this is just meant to give you some visual picture of what a neural net is and what training looks like. Okay. So I won't let this, so you can see it's getting better and better. Okay. So I just want to discuss a few simple examples in mathematics that I find very illustrative. And I should emphasize that I really don't think that we have enough of these. These just very simple examples that illustrate some feature. So if you want to learn about deep learning, typically there'll be some example like image recognition or something like that. But there's many beautiful examples in mathematics, also from pure mathematics. And I think that we should, I really feel that we need some kind of database of these good, simple examples because they're very illustrative. So before I get to these examples, I just want to kind of give the following picture of training. So I think it's very useful to think that I've drawn a picture on the left. So this is meant to be a high dimensional vector space, here represented as R2, broken up into kind of polytopic regions. And on each of these regions, we have a linear function. And the composite is piecewise linear. So we have a linear function on each piece, and they fit together to form a piecewise linear function. And what happens as we train is that these polytopic regions move around and the linear functions move around. Okay? And the other thing that's important to notice here is that there's kind of outside a small region, the learned function is rather boring. So all the action is kind of in a small region of the space. And you have to imagine that this is not going on in, so typically we would use these models in very high dimensional spaces. So this is not going on in 2-dimensional space, but rather in something like 10,000 dimensional space or something like that. So that's the picture. That's my picture of what happens during learning. So the following points are important, I think, when considering mathematical examples. So it seems to work best when the input dimension is high. So the complexity is a complexity from dimensionality rather than from, so typically deep learning would not work very well for learning, for example, a real valued function or something like that. The function is on the unit cube or some kind of good compact region inside a high dimensional space. And the coordinates have low symbolic content. So this is a term that I learned from the DeepMind researchers, which basically means that kind of messing with any of the coordinates individually won't significantly impact your function. So if you think about an image, messing with a pixel does not change the output of the function. So you can think about this as having learning functions that are reasonably noise tolerant or something like that. So I'm trying to emphasize this because this kind of immediately rules out a lot of extremely interesting stuff in mathematics. So it kind of immediately directs you towards things that are much more likely to be successful in mathematics. And somehow I should have said on my slide where I had the disclaimer, probably one of my greatest qualifications in giving this talk is that I've tried very many things that didn't work in machine learning mathematical stuff. So there's, if you kind of encounter this subject for the first time, there's all these YouTube tutorials explaining how this all works brilliantly. And then I try it on the first kind of example in mathematics and it just does not work at all. And I feel like I'm doing something wrong. And then slowly when I talk to experts, I realize that I've kind of attacked these particular functions that they're very noise intolerant. And so we expect deep learning to have a lot of difficulty learning them. Another point that I just want to say briefly is that, so in applied maths, there's this very important concept of cursive dimensionality, basically that there's an enormous amount of space, kind of a lot more space than I would intuitively expect in 10,000 dimensions or something like that. So for example, if I want to learn a function in 10,000 dimensions, you have to sample an incredible number of its values in order to have some kind of hope of accuracy. But what deep learning seems to do is it allows you to overcome this on certain classes of functions. Okay, so let us move on. So here's an example of a function. This is actually, so we ran this seminar last semester on machine learning for the working mathematician, come to grips with some of these things. And we were just kind of mucking around with simple examples. And this is one of the examples that we considered, namely learning the parity bit. Another example that we considered is learning the divisibility of a binary digit. So for example, I give you the binary expansion of a number between 0 and 20,000, and you should tell me whether it's divisible by 5 or something. And this is a typically extremely noise sensitive function. This is exactly the function that is kind of the checksum in signal processing. So it's very noise sensitive. And so you can learn this if you have a very, very large neural net, but it won't generalize well. And you'll feel like you're doing something wrong and you're not. So, and somehow it's very good to have these kind of examples in mind because many examples in number theory are somewhat similar to this example. Okay. So that's an example of something to stay away from. I want to give you another example that just shows how important representation is. So representation is basically you imagine, so I'm a representation theorist. It has nothing to do with representations in the sense of representation theory. Basically, the question is how do you encode your input that you want to make a judgment on? How do you encode that in a vector space? So in some cases, for example, in the case of image recognition, this is very kind of classical. But you might, for example, another thing that you might do is take your image and do something like a singular value decomposition and then feed those values in also. So these are called features, and the choice of features is extremely important, as the next example is meant to illustrate. So this is example, I love this example. It's due to a postdoc in Sydney called Joel Gibson. So we consider a permutation of n, and I want to list it out as, so x1 is what it does to 1, x2 is what it does to 2, xn is what it does to n. So I'm listing it in string notation. And there's two very basic subsets of 1 up to n minus 1 that we consider when studying the representation, considering the symmetric group. This is the right descent set and the left descent set. So in this language that I just, so in this string notation, the right descent set is those I such that xi plus 1 occurs, xi plus 1 is bigger than xi. And the left descent set is those I such that I occurs to the right of I plus 1. So imagine that you want to, you're given x1 up to xn as a point inside R to the n, and you're asked to write down hyperplanes which detect the right and left descent set. So the right descent set is very easy to detect. You namely just write down the hyperplanes xi minus xi plus 1. And this is positive or negative if and only if I is in the right descent set or not. But if you think about the left descent set, it's much trickier. You can think about it in examples, but it really seems like you need a lot of hyperplanes. You need to chop up your space in a complicated way. And so you would kind of expect intuitively that if you feed in x as a vector inside a vector space, just as in terms of x1 up to xn, then the deep learning will have a much better job at predicting the right descent set than the left descent set. So I kind of expected this to be the case, but I didn't expect how dramatic this is. So here's some fun little experiments that I did with Joel. So we have the right descent set, left descent set. Now, if we put the input vector in, so our representation of our permutation is just the vector x1 up to xn, here's what we get. So in predicting the right descent set, after 300 steps of stochastic gradient descent, it's predicting the entire right descent set right nearly 100% of the time. Okay. And after 300 steps of on the left descent set, it's getting 0 out of 5,000 right. Okay. This is a little bit more tricky task than the kind of tiger not tiger task, because you have to do a classification over all the integers from 0 up to n minus 1. But still, I was shocked at how badly it went on the left descent set. And this didn't look like it was improving. So I ran this, I ran 2,000 or 3,000 steps of gradient descent, and it didn't look like this was learning anything. Okay. However, now imagine that this was a problem in the real world. I mean, in a real mathematical world where we kind of didn't already know the answer. We could instead say, okay, we have a permutation. We've unfairly given this to the network. We should just give it to the network as a permutation matrix. And this is what happens when we do that. So there's absolutely no difference between left and right. Okay, so after 64, so I should say that this also starts to struggle on permutations of 50 elements, but here I dropped it down to permutations of 20 elements. This is surely just a question of size of my neural net and my ability to stare at my laptop at some point and watching it train. But for permutations of 20 elements, there's a complete symmetry of left and right. So this feeling that we're somehow biasing the network by giving it the permutation in a certain way is justified in practice. Okay, so that example is just meant to illustrate that how the input sits in the space, the representation really matters. And I don't know, I feel like these things may seem like technical curiosities, but I feel like to get any understanding of what is actually going on in deep learning in a kind of context of mathematics, we need a whole slew of these examples. So if you have fun examples, please let me know. I'd be very interested in compiling them at some point together with code that people can run. Okay, so now I just want to describe deep learning more from a kind of scaled out point of view. So I think that if you read the popular press about deep learning, and even I think some researchers will give you the impression that there's a vanilla structure like the one that I presented on the first slide, which is versatile on many problems. This is absolutely not true in my experience. So vanilla architectures usually only work out of the box on simple problems. And architecture matters. So there's many different architectures in deep learning. So for example, there's convolutional neural nets, which are very, very useful on graphics. There's transformers that are very useful on language. There's graph neural nets that are very useful on graph structured data. There's a whole slew of other architectures. And I think it's very important to be aware that we're learning some aspect of the problem, but we're also putting a lot of understanding of the problem into our architecture. So if you look at the paper on transformers called Attention is All You Need, you notice it's a remarkable architecture, and it revolutionized machine learning translation, but also there's a very subtle awareness of the particular demands of natural language processing, which is put into the architecture. Okay. So, if you ask someone on the street that knows about AlphaGo and AlphaZero, they'll almost certainly tell you that a neural net basically became world champion of AlphaGo. But if you look in more detail at the AlphaZero paper, an AlphaGo and AlphaZero paper, you'll notice this extraordinary tree search that's present. And if you just play against the neural net that powers AlphaZero, I would still lose. It's like bad professional, but it's really the tree search that takes it from the ranking. I think I don't have these numbers in my head, but I think it's from about ELO 3000 to about 5,800 or something. Like tree search does an enormous chunk of the heavy lifting. And yeah, so I think it's really important when we're thinking about like building architectures that incorporate deep learning into mathematics, that it might be possible to do AlphaZero like achievements in mathematics, but it's not going to be a neural net alone. I think you can see a similar thing with AlphaFold. So it's actually referred to in the Nature paper as a neural net, but I really don't think this is accurate. It's a whole lot of neural nets pieced together, also with other algorithms, which very much incorporate human understanding of an extremely difficult problem. So we are very, very far away from some kind of very generic learning architecture. So just some things that I wish I'd known 2 years ago when I began on this journey. One has to be ready to spend lots of time experimenting with model selection, learning rate, etc. There's no hard and fast rules about what particular model one should take or what dimensions one should take, etc. This is just learned by the neural nets inside our heads. And this is difficult, and it's really difficult, this thing of like, is this training for some fundamental reason, not training for some fundamental reason, or am I just being a bad person? And it's very useful to have someone who has background in machine learning. And this is, I think, another really important point which emerged with the work with DeepMind, is that we have to make a decision in every case. Are we trying to push mathematics or are we trying to push machine learning? So if you're trying to push mathematics, don't try to use a very sophisticated machine learning architecture. Try to use a machine learning architecture that's incredibly simple. So the examples that I'll discuss at the end use vanilla supervised learning in 2 cases, and the absolute simplest reinforcement learning architecture in the 3rd case. And it's interesting historically that AlphaGo began as a supervised learning task, namely looking at a whole lot of Go history. Am I able to train a neural net to predict a move that a good player would make? Okay, so it's often starting with these simple tasks that lead to insight. And also it's so I've had about 50 people come up to me and say, let's use AlphaZero on problem X. And this has been tried at DeepMind on a number of problem X's, and it has not worked. And so we're not yet in even close to a situation where you can start with some very vaguely defined problem and throw a neural net at it and have it solved. Okay, so I just want to also comment briefly on scale. So this is something that took me a rather long time to understand. So basically it's kind of cultural difference between mathematicians and machine learning researchers. So I, as a mathematician, would like the simplest example that illustrates some phenomenon, whereas I often find machine learning researchers want to immediately increase the model size greatly, and in my opinion, increase the complexity greatly and decrease greatly my ability to understand anything. But there is something in this instinct which is basically that it works. So there's important kind of history here. So scaling up neural nets works. And there's also very interesting mathematics going on here, and I won't discuss this. I'm not discussing any aspects of kind of mathematics of machine learning in this talk. So the history is one of the major kind of moments in this was this AlexNet, which was from around about 2012. So this was on this ImageNet database, which is about, I think it's something like 14 million images divided up into 100,000 categories. So you have a category for elephant and truck and that kind of thing. And you would like a model which with some accuracy predicts what category your image belongs to. So this was a kind of grand challenge in machine learning in the 2000s, which nobody could get near. And this AlexNet that was written by the 3 authors who are displayed there, they basically decided just to fix a pretty simple convolutional neural net architecture, but make it much, much larger than had ever been attempted before. And they really focused on the engineering aspect of the problem. So they write at the end of the introduction of that paper, all of our experiments suggest that our results can be improved simply by waiting for faster GPUs and bigger data sets to become available. Okay. And that prediction has very much come true. So I'm sure, yeah, I sadly could not come to any of the talks yesterday, but I'm sure GPT-3 was mentioned, this large language model. And then recently we had DALL-E and DALL-E 2. And now these are incredibly large models that take months to train, and they do seem to show some kind of emergent capacities. There's really striking things that occur at enormous scale, which I think is still poorly understood. And this is, I'm just mentioning this because this is the bit of the future which I think is incredibly difficult to kind of foresee. So everything about the future is difficult to foresee, but the role that large scale of neural nets in mathematics will play, I think, is very difficult to imagine. Okay, So now I just want to discuss 3 examples in mathematics. So these are examples in knot theory, representation theory, and graph theory. And apologies to Akshay because he's heard 2 of these already, I think, in much more detail than I'll give here. So knot theory. So here's a knot. And there's many connections to different fields. So 3 and 4D topology, hyperbolic geometry following the extraordinary work of Thurston, quantum topology, mathematical physics, etc. And these are all enormous subjects, and it's foreseeable that there's connections between these subjects that we have not yet seen. I guess one of the things that's happening now is that mathematics is occurring on such a scale that it's impossible for any one person to be on top of kind of everything displayed on this slide. And I think Buzzard tells a similar story about his realization that there was an open cover of a theorem in number theory. It was just that the experts knew complementary facts, and he was able to put these together. So to a knot, we can associate a whole lot of invariants. And I think it's a very reasonable question to ask, do there exist unexpected relations between these invariants? And this is what the DeepMind researchers together with Mark Lackenby and Andras Juhas did. So they tried, basically they gave the neural net a few of these invariants and then asked it to predict another one and saw how well it did. And in particular, when predicting I can't remember what. Yeah, so sorry, I just blanked on what exactly they were predicting, but they noticed that a whole lot of, so on the top right is a saliency plot. So these are various measurements of the hyperbolic geometry of the knot. And you can see that various of them are showing up rather strongly in the prediction of the signature. That's right. So the signature is on the left. And so based on this, and then with an enormous amount of work, they were able to prove a theorem connecting a 3 and 4D invariant to a hyperbolic invariant. So the signature on the left and the slope, which they define, is controlled by the hyperbolic volume and the injectivity radius. So this is definitely something that I think has more potential. Just kind of running neural nets on large scale databases and seeing if there's interesting connections. It's also interesting in this process because you need a mathematician to detect interest here. So some of these relations will be obvious and known, and some of these relations would probably be something like equivalent to the Riemann hypothesis, and so you want to stay away from those. But the trick is to find the interesting ones, and then we need a measure of interest, which is also, I believe, exactly what the next talk is about. So the project that I worked with DeepMind on was in representation theory. So we have these beautiful things called Cauchy-Lutzyk polynomials. So here's an illustration of them developing for the affine Weyl group of type G2. So these are their values at 1, but you get this incredibly beautiful, complicated structure, which we're a long way away from understanding. And there was a conjecture which has fascinated me since I was a graduate student. Fascinated me in a kind of idle way, in the sense that I had no kind of attack on this conjecture at all. So this was made by Matthew Dyer and George Lustig at the beginning of the 1980s. So to a pair of permutations, you can associate this Cauchy-Lutzyk polynomial on the right. So this is a kind of very deep measurement of X and Y. It seems to be, so its presence in representation theory indicates that it's a very kind of fundamental but difficult quantity. And you can also associate this kind of much more elementary quantity known as the Bruchar graph, which is basically essentially related to the Cayley graph of the symmetric group with generators given by the transpositions. And it's somehow like the part of the Cayley graph that sees the interval in Brouhar order between the two elements. So the Brouhar graph is kind of complicated. Like it's a complicated thing that's immediately associated to X and Y, whereas the Cauchy-Lipschitz polynomial is a deep and simple thing. And I was imagining that somehow so the conjecture is that you can pass from this Brouhar graph to the Cauchy-Lipschitz polynomial. And I should say, it's just an interesting conjecture. I've been interested in it for some time, but it's something that doesn't have like a particularly compelling reason to be true. And I had no reason to kind of ever work on it because I saw no reason to, no way of establishing it. So somehow the idea is like, I don't know, I was kind of imagining this Brouhar graph as being some object of nature, where if I'd played with it enough, I'd just be able to read the Cauchy-Lipschitz polynomial off very easily. So what we did was we trained a particular neural net architecture called a graph neural net to predict the Cauchy-Lipschitz polynomial from the Brouhar graph. Amazingly to me, it was able to predict with extremely high accuracy very quickly. So I think it got to 97, 98, 99% within a very short amount of time. But then you can do a saliency analysis of the model and ask what is it kind of looking at in order to make this decision. So what happens in a graph neural net is a whole lot of, so you start off with certain vectors at the nodes of your graph, and then these are passed around by certain learned matrices, passed around the neural net according to the edges of your graph. And then you get certain new vectors, and then you do some kind of pooling operation to produce a list of scalars from which you read the Cauchy-Lipschitz polynomial. And the point here is that you can look which vertices kind of carry a lot of weight in this measurement. So which vertices, if I removed, would change the output of my model. And this led us to this plot on the right-hand side, which shows a very strong correlation between what the neural net is looking at and something which the neural net is not actually allowed to see. So it seems to be somehow guessing a labeling of the edges which it doesn't see. That's what's happening on the right-hand side. And after staring at this for some time, so it suggests breaking up, that plot on the right suggests breaking the graph on the left up into these two pieces, the red dots and the blue dots. And this then leads to a conjectured formula that would solve this Cauchy-Lipschitz, this combinatorial invariance conjecture. And also, subsequently, I was able to prove this conjecture in an important special case. So it gives a new formula for Cauchy-Lipschitz polynomials, which came from staring at these saliency plots. So here's a picture of kind of what happens. So here's an example of a Brouhar graph. And then you can ask, basically, after some cooking, you can ask which edges are the most important, and you get a plot like this. Okay, so you go from a graph like this to a graph like this. And now if you stare at this graph, you notice certain like very dominant cube-like structures, which leads to these hypercube decompositions. I also just want to go back to I had no idea. It was just kind of luck that this worked, I think. There was no particular insight in choosing this particular problem. But a posteriori, I think it's clear why this is a good problem to train a neural net on. Namely, I suspect that this graph is very noise resistant. Namely, that adding or deleting an edge will not, doesn't have a big effect on the Cauchy-Lipschitz polynomial. And similarly, back in the knot theory situation, one imagines that the kind of relationships between these invariants, like the ones encapsulated in the theorem, are very general statements across all knots and are rather noise resistant. Okay? So we're not using neural nets to pick up kind of needle in a haystack specific aspects of a situation. It's much more kind of large scale structure. Okay, so now I'll go to the last example, which is this is this beautiful work of Adam Wagner. So I'm not a graph theorist, but graph theorist tells me that the subject is full of conjectures, and someone has the sense that they're true for rather deep reasons, but some are just false, and we'd like to kind of stop worrying about them. And I think this was Adam's motivation in doing this. It's very difficult to find counterexamples to some of these statements. So the space of graphs on the number of vertices on the left is larger than the number of board positions in Go. So it's that you're looking at an enormous space of graphs, and it's very difficult to isolate particular graphs inside there. So what Wagner noticed is that you can play a game. So this is in the setting of reinforcement learning, where the model's aim is to minimize or maximize a certain quantity in order to refute a conjecture. So the model here is very simple. So what we do is we give, on the left, for example, we imagine all possible edges in the graph. So we take the complete graph on the vertices on the left, and we give each of the edges to the computer one by one, and we say, do we want it, yes or no? And initially, the computer samples choices of these edges randomly. And then at the end, it gets a reward based on a conjecture. So here's a conjecture which Adam believed was not true. So it's not important what the conjecture is, it's just important that it's framed as an inequality. So something is bigger than or equal to something else based on a connected graph with more than 3 vertices. And so you can take the left minus the right-hand term and try to minimize it. And if you get it below 0, you'll have found a counterexample. So we have a quantity, we let the computer sample, and then you use samples which led to low values as supervised data for a training, to retrain your neural net and retrain your selection policy. Okay? So each new choice of an edge in the graph is conditioned on the choices that it's already made. So this is called the cross entropy method in reinforcement learning. It's one of the simplest methods of reinforcement learning. Okay, so here we watch it run. So this is the, so I guess that you'll see a video, it contains about 40 or 50 frames, and each frame consists of one sample from the current distribution that the computer believes is going to maximize or minimize the reward. So here we go. So over time, you can see this converging to a very clear kind of structure. And then Adam, in this particular case, plugged this back, computed the 2 terms, and realized that this is a counterexample to that conjecture. Here's another example. This is a little bit more of a complicated one, but again, we have an inequality that we're trying to violate. So we just want to try and minimize the left-hand term, and here we'll see it running. Okay, so at that point, you can see that there's a very obvious structure emerging. So this is not a counterexample, but what Adam is able to do is see, okay, there's a clear structure here. What happens if I put 50 of these petal-like structures around the central node and extend these arms to be very long? And then he gets a counterexample. Okay. So yeah, I want to emphasize that these 3 examples are very kind of tentative explorations of machine learning in pure maths, but I think that they're interesting. So I will summarize with the following points. So neural nets perform some tasks remarkably well, and they appear to be strongest on tasks that are simple and intuitive for us. And I just want to really emphasize this point, that most applications of neural nets to difficult problems incorporate them into more complicated architectures. So the example of in representation theory, predicting causality polynomials, it's a reasonably simple use of machine learning, but it still uses graph neural nets that are rather complicated beasts. And so we're already encoding a lot of the problem into the neural net architecture. Okay. So if we're going to see major applications of machine learning to difficult problems in maths, I would anticipate it appearing as part of some more complicated strategy. So neural nets appear to provide very useful tools for conjecture generation and refutation. I also think that there's a lot of potential for applications in organizing calculation. So a simple example of this is you might have 3 different ways of computing something. All of them give the right answer, but some of them are much more expensive on certain inputs. And you could imagine having a neural net deciding which inputs to use, which algorithm to use based on the input. And also guiding search. So often when you have a search problem, which is very common, for example, in some aspects of combinatorics, you can try some kind of random search, but if you have some very weak heuristic, this can be extremely powerful. You know, a tiny little bit of light is a lot better than no light at all. And you can imagine neural nets providing this tiny little bit of light. And I see little evidence that neural nets are capable of replicating the system to parts of the mathematical process. So we can predict everything except the future. I thought this was from Oscar Wilde, but then my friend told me that he read it on a fortune cookie in Sydney. So thank you very much.